All right, so hydrogen typically makes one bond. So this is what I write, just one dot in the symbol. Helium is an exception to a rule in that noble gases tend to have 8 electrons around them in their valence. Helium obviously only has 2. So when I write that on my periodic table, I might put parentheses around it just because it does violate a rule here. Helium only has 2 electrons, but it is a noble gas. This is a full shell. It's not reactive, and it belongs in group 18. It's not going to do any reacting. It literally just bounces around in this state, perfectly unreactive. Okay? So that's an exception. It has 2 in its valence, even though it's a noble gas. All right. Beryllium is in group 3. How many electrons should it have in its valence? Beryllium, is in group 2. How many electrons should it have in its valence? 2, because it's in group 2. Okay? So I'm going to write 2 dots, and that's representing those 2 electrons. Why did I write them together, paired up? Because they fill one orbit, exactly. One up, one down. They're in the 1s, or the 2s, rather. 2s. One up, one down. All right, so that's why I drew them like that, paired up together. When you get to boron, the situation gets a bit more complex. There are 3 in the valence, right? And you might think to write them like this. 2 that are paired up, because that's the 2s, one up, one down. They're in the same orbit, so they should be paired. And 1 lone electron. The problem with this structure is it makes you believe that boron's only going to make 1 bond, right? Because lone electrons are opportunities for bonding. So that's actually not correct. Boron tends to make 3 bonds. So here's why. If I do the full electron structure for boron, it has 5 protons, 5 electrons in the ground state. All right, so the 1s2 is full, and then the 2s2 is also full, one up, one down. And then the 2p has just 1 electron in it, but there are 3 orbits. There's 1 electron in the first one. As an electronegative atom comes in proximity to this boron, this electron will get promoted to an empty p orbit. All right, so this electron right here, you draw it in a different color, this electron gets promoted to this empty p orbit. It only costs about 20 to 40 kcal per mole to get this done. It does take energy to accomplish this, but it's really just a little bit, 20 to 40 kcal per mole. Kcal is just like joules, it's a measurement of energy. All right. It takes a little bit of energy to get this electron out of that orbit and get it into this empty p orbit. However, every time you make an additional bond, you can get about 100 to 200 kcal per mole in stability. So the exchange is very spontaneous. You're going to actually make this thing way more stable by creating an extra bond. All right, so this electron is promoted to an empty p. So the configuration that you're going to draw on your table is actually this. Boron with 3 lone electrons. It's going to make how many bonds? 3. All right? The situation for carbon is completely analogous. All right? You would think to draw it like this. 2 paired up in the 2s2 and 2 lone electrons. However, let's change this configuration just slightly. All right, this is carbon. There's 6 electrons in the ground state. And all I'm going to do to this configuration is just put an extra electron in here. It's a 2p2. Oh, here we go. 2p2, and I'll put 1 right here. Okay. So when I promote, there's still an opportunity to promote an electron here to this orbit. See how this 2p right here? That's empty. So I can promote this 2s to the 2p, spend about 20 to 40 kcals, and make an extra bond, and I get 100 to 200 kcals per mole in stability. All right. So this is going to make an extra bond. So carbon is actually going to look like this. 4 lone electrons. All right. Write this on your periodic table above carbon, group 14. Everything in group 14 is going to have the same electronic structure. So it's going to have the same, this is called electron dot structure. Everything in the group has the same electron dot structure. You, therefore, only need to know 8 dot structures to do every Lewis structure in the world. That's important in chemistry.
Wait, each group has the same dot.
Yeah. So hydrogen, everything in group 1 is going to have 1 dot next to the symbol. Cool. All right. So that's carbon. That's the hard stuff. When you get to nitrogen.
Wait, why didn't you say this before? Like while we were doing that other lesson, the other. Like,
That was just an intro. We're just going in more detail now.
So I was struggling, and all you had to say was this, and I would have known it.
All right. Well, now I'm getting you back on board.
Just
All right?
messing with you.
Cool. So nitrogen has how many electrons in the valence?
Wait, say it again.
Nitrogen, how many valence electrons does it have?
Is that 5?
5, because it's in group 15. It has 5 electrons in the valence.
You basically kind of just take the one away in a sense. Like when you have because the group 17 they have 7.
Right.
structures.
Exactly. Yep.
So
You're
you
just taking that number from the group. Exactly. So hold your question for 1 second. So 5 electrons in the valence. You would be tempted to draw it like this, and you'd be right. And here's why. There's no MTP orbits available for promotion. These paired up electrons up here, they can't get into an MTP in order to make an extra bond. It is what it is. There's no MTPs to do that. So it's going to make how many bonds?
5, 6,
3. 3. There we go. All right. 3. Why? Why 3? Because there are 3 lone electrons, right? So it's going to make 3 bonds.
If I put the 2 dots at the bottom instead of at the top.
Doesn't matter. Doesn't matter.
Okay.
What all that matters for is if you were going to bond this to something like on the quiz, all right, the homework quiz, we did NF3. That's nitrogen trifluoride, right? Nitrogen trifluoride. If I were going to put fluorines next to this, I'd draw right here, here, and here. Because these are the opportunities for bonding. These lone electrons are opportunities for bonding. So it wouldn't make any sense for me to write the F up here next to this pair. Wouldn't make any sense. All right? So that's nitrogen's electron dot structure. Write that on your periodic table. You got it? So everything in group 15 has the same structure. What about oxygen? It'll have 6. 2 paired up and 2 alone. All right. That's the entirety of group 16. Identical. Yep.
Do you have the pairs in any?
Oh, yeah. So the pairs will be in any configuration. It doesn't really matter. I tend to write them on opposite sides of the atom for a very important reason, though. Electrons tend to repel each other, right? And it turns out that when this does its bonding, those electron pairs will push on each other with repulsion, and they'll get as far away from each other as they can. So it actually kind of makes a little bit of geometric sense in 3 dimensions to put them on opposite sides. Okay. That's a little bit more advanced. We're not going to get to geometry for a while, but that's why I'm doing it. All right. So what about fluorine? How many electrons in the valence?
7.
Exactly. All right. So that's it. 1 opportunity for bonding. 1 lone electron. What about neon? Everything's paired up, right? It's going to have 8. This thing doesn't bond. Neon does not bond. It's completely stable as it is. It's a noble gas. It's a group 18. All group 18 elements except for helium have 8 electrons in the valence. This is called the octet rule. Every element on the table is going to react in order to achieve 8 valence electrons. They all want to look like the noble gases in group 18. So the octet rule is just expressing this idea. It's telling you the goal of bonding is to achieve 8 valence electrons. You got that somewhere in your notes? goal of bonding is to achieve 8 valence electrons. That's called the octet rule.
Can you repeat that?
Yep, the goal of bonding is to achieve 8 valence electrons. That's what the octet rule says. Yep.
8. Wait, can you say that again? 8.
What about group 9?
How would you do a Lewis dot connect one of those?
Simply, actually. It turns out that group 9 has very nearly filled the D, right? But it's only got 1 electron in the S, the 4s. So that's what you'd write. In fact, cobalt, a fairly common oxidation state for cobalt is just 1 electron. So you could write it this way. The reason we don't write it that way is because the energy levels are so close together that boosting another electron out of the D is doable. So it could actually have a 2+. So I could also write it like this. And so since there's not 1, we don't write it. We just don't tend to write Lewis dots for transition metals. So what we're getting at here is that cobalt can make 1 bond, but it could also make 2, it could also make 3. It could make as many as 9 bonds. All right. It could share as many as 9 electrons with other cobalts in its vicinity. Yep, it's very unlikely. It's very rare, but that's the most. That's the most that any element on the table will tend to lose. It's very energetically unfavorable. It doesn't happen a lot. All right. So did we get everything? Let's do the quiz. Well, actually, we already did the quiz, didn't we? Right? Nitrogen, it's bonded to fluorine. There's 3 of them. What's this thing called? What's this thing called? Nitrogen trifluoride. Okay? I have to express that there's a lone pair on nitrogen. Okay? That goes here. Count up the electrons. 2, 4, 6, 8 around nitrogen. There's the octet rule is being satisfied here, right? Nitrogen bonded, and it has 8 electrons around it. Notice that each line represents 2 electrons. Each line represents 2 electrons. They're being shared between the 2 elements. That's what the line represents. It's a covalent bond. If there's not a covalent bond, if you do the electronegativity difference, and you use the scale on page 194 of your text, the Pauling scale for electronegativity, if you calculate the difference and it's ionic, you do not write a line. You just give the electron to the more electronegative one, in this case fluorine, and you'd write negative next to fluorine and positive next to nitrogen. You don't write a line if it's ionic. Okay? The line represents sharing. Is this a complete diagram? Am I finished?
No.
Why not? I haven't put any electrons around fluorine, and if you count, it only has 2. That's a problem. Right? How many electrons should there be around fluorine? 7 total, so watch. Count them up. 1, 2, 3, 4, 5, 6, 7. That's how many is normally there, right? 1, 2, 3, 4, 5, 6, and 7. That's how many is normally on fluorine, so it doesn't have any formal charge. I'm not going to write a charge next to it. If I erase one of these electrons, I have to write this. I have to write a positive sign next to it. That's called formal charge. If it's missing an electron, it becomes formally positive. If I write an extra electron on it, it's formally negative, and so on. All right? If you count these up now, including the line, it's 2, 4, 6, 8, if it satisfies the octet rule. All right, same thing on fluorine. So all of them now satisfy the octet rule. You have to do a little bit of the counting with electrons. How many electrons are there on fluorine in general?
No.
In the valence?
No, 7.
7. How many fluorines do we have? 3. How many electrons is that total? 21. How many nitrogens are there? 1. How many electrons on nitrogen? 5. Okay. I I add these two up, what do I get? 26 total electrons. Let's count them up. Ready? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, there are 26 electrons. I'm done. This is correct. I've accounted for all of the electrons. Did you notice that there's no charge on this? When I wrote the molecular formula, I wrote NF3. There's no charge right here. It's 0. So there should be exactly 26. If I wrote this, if I wrote 2 plus, I'd have to take 2 electrons away somewhere. And there would have to be 2 missing, and there would have to be formal charges in the diagram to account for the 2 plus molecular charge. All right? If I wrote 2 minus, I'd have to account somewhere for 2 additional electrons. Okay, so there'd have to be 2 additional electrons somewhere on the diagram. So I'll put those 2 back. There'd have to be 2 additional somewhere, so there'd have to be a double bond. Something like that. Okay? This wouldn't happen, of course, not with fluorine. But there'd have to be additional electrons on the diagram somewhere to account for that 2 minus charge. What's up, Jeff?
When you take away electrons or atoms, no matter where.
Yes, it does. Generally speaking, electronegative molecules are going to end up, if there is additional charge in the diagram, it'll be on the electronegative ones, right? Because they tend to gain electrons. If there's an electropositive molecule in the diagram, like in this case, nitrogen is less electronegative than fluorine, you tend to put positive signs on the nitrogen, negative signs on the fluorines. All right, that's what will tend to happen. All right, the other question was about, on the quiz, was chlorine, right? It's just chlorine gas, Cl2. That's really simple, right? Just one single bond between 2 chlorines, and you fill in the electrons like that. See how they each, now they satisfy the octet rule, right? 2, 4, 6, 8. No formal charges. What's the electronegativity difference between the two? What's the difference in electronegativity between these two? 0, exactly, which is a non-polar covalent. I don't have to write anything. No formal charges, no partial charges. Okay? So, from here on out, here's what you need to do. Just try these examples on the sheet I gave you. Try the highlighted ones first. This is linked on Google Classroom. All right, try these.
Did you give us a sheet?
No, I'm working on it. All right, so try these, and it's on Google Classroom. Don't lose it because we're going to be working on it for the rest of the week.